Today we're going to go a little further with acids and bases and look at some of the calculations that surround acids and bases. So to begin with, alright, our hydrangea flowers. Those are flowers that change colors based on pH. So remember, lower pHs were the blue ones, the pink flowers were the higher. That's actually opposite of what's called litmus paper. Litmus paper, if it's going to turn red, then that means you've got a low pH, it's acidic. If it turns blue, it's basic. Okay, so flowers are kind of the opposite of litmus paper. But that led to our pH scale, which we see here. Strongly acidic would be the low pH, which means you've got a high hydronium ion concentration, whereas a high pH, pH 12, 13, 14, that means you have a high hydroxide concentration. So if we kind of look at these little scales that we looked at before, the one that has a greater hydronium concentration are your acidic species, your acidic solutions. Those that have a higher concentration of hydroxide are more basic. Okay, so you still have some acid base present in both, but it's just a question of which one has a greater concentration, a higher molarity of these species. So our pH scale, it's used to describe the acidity of a solution. So what pH literally means is it's just a way of representing the concentration of hydrogen ions, but on a logarithmic scale. In the same way, pOH, so the negative log of your hydroxide ion concentration, that literally means the concentration of hydroxide ions represented on a logarithmic scale. So with that, we have our acidic pH is anything that's less than 7, our neutral pH is equal to 7, and our basic pH is 7, or greater than 7. So if you look on the right-hand side, we have our scale here of anywhere from, we've got a -1, so there are some negative pH units, but we won't really discuss those. We'll mainly just talk about going from a pH of 1, of 0, all the way up to 14. And that's your natural pH scale. Okay, so you've got your acidic substances on the bottom, lemon juice, soft drinks, beer, vinegar. Your basic ones are more like baking soda, ammonia. Oven cleaner is extremely basic. Okay, so all of these are present in our homes. And so whenever you say like baking soda, what that means is it's got a higher percentage of your basic species in solution than you have of your acidic species. So this is the litmus paper I was telling you about earlier on the right. That if litmus paper turns red, so that's what you see on the right-hand side in picture B, then if it turns red, that means it's acidic. If it turns the red litmus paper blue, it means it's basic. And it's a very good test because it quickly tells you if it's acidic or basic, but it doesn't tell you the exact number. The other way to determine pH is a very quantitative type of measurement where you stick a probe down into solution and it responds to the concentration of hydrogen ions. And the higher your hydrogen ion concentration, the lower your pH will be represented on the pH meter. And that's basically responding to a potential gradient across the electrode, but we're not really going to get into how that works. Okay, so logarithmic scale, what that literally means is for every change in pH of 1, you're changing the concentration of your hydronium ion tenfold. So to go from a pH of 4 to a pH of 3, that's 1 pH unit change. pH of 4 is 10 times smaller than a pH of 3. And pH 3 has 10 times less hydronium ion concentrations compared to pH of 2. So as you decrease your pH, you are significantly increasing your concentration of hydronium ion concentration. So notice there on our second column here, your hydronium ion concentration, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. If you represent each of those in decimal form, that kind of helps you see that yes, indeed, each of these is getting bigger. So let's write, and let me pick out my pen. So 10 to the minus 4, how would we write that? 0.0004. Wait, not 4, sorry, 1. Let me erase that. Erase. So 10.0001. And then 10 to the minus 3 is 0.001. 10 to the minus 2 is 0.01. So notice each time it's a tenfold concentration change. So whenever we're looking at logarithmic ways of looking at a sample, every pH unit change of 1 results in a tenfold change in your hydronium concentration. Alright, so here are these numbers represented on the scale. So remember, acidic is on our left, basic is on our right. So note the correlation here, that if you look at the hydronium ion concentration, these numbers that are circled directly relate to the pH. So if you have a pH of 1, what does that mean? Your hydronium ion concentration is 10 to the negative 1 molar. If your pH is 3, that means your hydronium ion concentration is 10 to the negative 3. So these numbers that are circled directly correlate with our hydronium ion concentration. And they're inversely related to your hydroxide ion concentration. So notice that as our numbers get smaller going this direction for our acids, our numbers get bigger going this direction for our bases. So these guys are all bigger numbers, and these numbers are all smaller. The number one error I'll typically see in this is that you'll think, oh, 10 to the minus 14, that's bigger than 10 to the minus 1, but they're not at all. If we write them all out in decimal form, once again, you can kind of prove that to yourself. So for instance, 10 to the minus 14, how could we write that? 0 point, and then we need to draw 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then there's our 1. So that's 10 to the minus 14. While 10 to the minus 1, what does that mean? 0.1. So a lot larger here, a lot smaller down here. Okay? And what I mean by the fact that they're opposite is the 14 corresponds over here. 14 minus 14 gives us 0. 14 minus 13 gives us 1, and that gives us our number here. And so what that lets us do is that's kind of the first calculation that we can utilize for pH calculations, is where did this 14 minus come from? Meaning 14 minus 11, that leaves us with 3. And that's our concentration here. So what can we say? Why does that matter? Okay. Why it matters, because of all of these calculations, you basically can go from pH to pOH and back and forth. And then you also can relate both of those to hydronium ion concentration and hydroxide ion concentration. So this first equation right here that you see, pH plus pOH equals 14. That's the one I just talked about. Whereas if you know your pH, then you also can figure out your pOH. Meaning, let's say your pH is 8. 8 plus 6 gives you 14. So that means 8 must be your pH. Your pOH must be 6 to give you 14. So you can directly relate pH and pOH to each other. Alright, similarly, hydronium over on the bottom right, hydronium ion concentration correlates really well with hydroxide ion concentration. Notice this 10 to the minus 14? That's why you're able to have the pH scale of 14. And the reason for that is this number that you see here, 1 times 10 to the minus 14, that's the kW of water. So what that is this is basically tells us a little bit about equilibrium conditions of water. The idea is if you have H2O in solution, and you have 2 of them, let's say, they're naturally going to spontaneously be reacting together to produce your hydronium ions and your hydroxide ions. So because of this, we just get this nice equilibrium where if you ever multiply your concentration of your hydronium ion concentration by your concentration of your hydroxide, it always equals 10 to the minus 14. So that's kind of where our pH scale comes from, is from the fact that our pH is related to concentrations in water. Okay. You can also have your pH in other things, but this is where the scale comes from. Okay, so those are the first two main ones. Additionally, though, we can relate our POH to our hydroxide concentration, and we can relate our pH to our hydronium concentration. So let's look at the one on the top first, so the other blue line. So POH always equals negative log of OH. 10 to the minus POH equals our concentration of OH. Why is that? Okay, so let's start out here first with POH equals negative log of hydronium ion concentration. Okay, if you take both sides and raise both of them to 10, well, first off, let's get rid of this negative. Move that negative over here. I'm going to do that first. Okay, so that one goes away. So what that means is 10 raised to the log, those two cancel out, and that's just algebra rules. So 10 to the negative POH is equal to our concentration of hydroxide ion. So we can use that to go back and forth. So either if we know our POH, we can figure out our hydroxide ion concentration. If we know our hydroxide ion concentration, we can figure out our POH. We can go back and forth. It's the same way down here for pH. If we know our pH, we can figure out our hydronium ion concentration using this equation. If we know our hydronium ion concentration, we can figure out our pH. We can go back and forth. Alright, so let's look at some examples of this. Okay, so let's say we've got 3.75. These are all the possible equations that we could use. So it's a question of where do we want to go from here? So if you look, if you start out with pH, pH is only connected to two things. It's connected to POH, okay? And it's also connected to hydronium ions. So that means we can go and we can figure out POH directly, and we can figure out our hydronium ion concentration directly. We can't figure out our hydroxide ion concentration yet. We have to first figure out one of the other two before we can figure it out. So that's kind of what I think about. Whenever I'm going to solve these types of problems, I first ask myself, what can I figure out based on my known information? And then do that, figure out if I can figure anything else out, and it's more of a stepwise manner. So let's do this one. Okay, so I said I want to do these equations. So I said I want to use all of these to help figure out the thing. So first off, I can use pH to figure out POH, because POH equals 14 minus our pH. Then, after I know my POH, I can use POH to figure out OH, our hydroxide ion concentration, using this equation. Then, after I know my hydroxide ion concentration, I can use it to figure out my hydronium ion concentration, using this equation here. Okay, and that's basically what you have to do, is all of these equations are here to help you convert from one species to another. So let's do this one. So just to give myself a little more room, I rewrote this but only showed you the ones that we're going to be using. So first off, POH equals 14 minus our pH. And our pH in this instance is 3.75. And in our answer, we're just going to keep the same number of sig figs. So 14 minus 3.75 gives us 10.25. I'm not really going to be concerned about sig figs on the exam. Okay, but this is just kind of how you would do it in real life. So what that means is your POH is going to be 10.25. So let me fill this in. Next, you want to convert from POH to hydronium ion concentration. So my hydroxide ion concentration equals 10 raised to the negative POH. So in this case, my POH, which I just figured out, is 10.25. So if I type that into my calculator, my hydroxide ion concentration equals 5.62 times 10 to the minus 11. So that's the second thing I figured out. So let me type this in up here. 5.62 times 10 to the minus 11. Alright, I know that. So now I'm going to follow my last arrow, because my hydronium ion concentration is the last one to figure out. So hydronium ion equals 1 times 10 to the minus 14 divided by my hydroxide ion concentration, which is 5.62 62 times 10 to the minus 11. If I type that all into my calculator, come back over here, it is 1.78 times 10 to the minus 4. times 10 to the minus 4. Okay, so that's just kind of what you want to start out doing. And then you kind of want to look back and see if your numbers make sense. What I mean by that, you know your pH plus your pH should equal approximately 14. Do they? Yes, you're good. Then you also know your hydronium ion concentration is related to your pH. So what I do, my pH is about 3.75. That's about 4. So if you look at your exponent on your hydronium ion concentration, it should be approximately -4. Plus or minus 1's okay based on whatever number's in front of it. But if I got -8 on something like that, it doesn't make sense because your pH should match your exponent for your hydronium ion concentration. Okay? And then if you add your exponents together for your hydronium ion concentration, they should equal approximately -14. -15 is pretty common too. So all of these numbers make sense. I did my math right. We're good to go. So let's do another example. The main thing to look at is that you just want to use the equations that you need to get the job done. So here I start out with hydronium ion concentration. So basically with hydronium ion concentration, I could either figure out pH or I could figure out hydroxide ion concentration right off the bat. I can't figure out pOH though. And so that's something I have to do next. I'd have to figure that out. Is going, okay, which one can I use to figure that out? Because with your pOH, you can either get it from pH, which I have designated here, but I also could figure it out via hydroxide ion concentration if I wanted to. We're just not going to do that for this. So let me go ahead and erase that. But you could if you wanted to. So I just wanted to point that out. Alright, so let's do these examples. So first off, I'm going to start out with my arrow to the left, which is hydroxide ion concentration equals 1 times 10 to the minus 14 divided by my hydronium ion concentration, 1.5 times 10 to the minus 9. Put that in my calculator and solve, and I'm ending up with my hydroxide ion concentration equals 6.7 times 10 to the minus 6. Let me fill that in up here. 6.7 times 10 to the minus 6. Okay? Next, use my hydronium ion concentration to figure out my pH. So my pH equals negative log of my hydronium ion concentration, which is 1.5 times 10 to the minus 9. Now I need to go put that into my calculator, and I end up with my pH should be equal to 8.82. Put that into my table. So that is my pH. And notice, I haven't been writing the units because the units were given in the table. But if the units were not given in the table, the units on my concentrations are all molarity. My units for my pH are no units. There are no units for pH or pOH. So my next step, I've got my pH. I need to figure out my pOH. So pOH equals 14 minus our pH, which is 8.82. I'm just using this equation up here. pOH equals 14 minus 8.82. So pOH equals 5.18. And I fill this in up here, 5.18. Alright, so now I double check myself, see if it makes sense. pH plus pOH, about 14, check. My hydronium ion concentration exponent's minus 9, that's approximately 8.8. Good, so everything looks pretty good. So this is kind of just the way I think about doing this. We have all these equations that relate hydroxide ion concentration to hydronium ion concentration, to pH, to pOH. It's just a matter of using the proper pH or the proper equation that gets the job done.